I am constructing the Hamiltonian of this material. Okay, till now you know Hamiltonian, okay, of particle in a box, Hamiltonian of hydrogen problem, Hamiltonian of harmonic oscillator. I think that much only you know, quantum. Okay, now I am constructing Hamiltonian of a real material. Okay, so now kinetic energy of ions plus kinetic energy of electron, then potential energy. Okay, potential energy means it is nothing but how potential energy looks like, V equals to E square by Ri minus Rj. I think you know this, right? Okay, this is a Coulomb potential. If there are two charges, how they interact. Okay, now how many potential is there? How many potential is present for this crystal? There are three potential. Three potential in the sense potential energy between ion and electron, potential between ion and potential between electron and electron. Okay, so this is the complete Hamiltonian of a system. Any system, this is so general, it is applicable for any system. It is applicable for your nuclear system also. Okay, so but question is, so I told you I am doing DFT, density functional theory. Okay, I am trying to study this material. Now my first assumption will come. Okay, what I assume in physics we assume, right? In physics we assume, what I will assume, my ions are not moving. Ions are fridged, it's sitting at the same place. When ions are not moving, then what is the kinetic energy of ion? 0. So kinetic energy of the ion 0, that means I can get rid of this term. Okay, then if my ions are not moving, then what is the potential energy between ions and ion? Is it 0 or it is a constant term? Because since the distance is constant, because it is not moving. Since it is not moving, so constant distance, so my energy is constant. Okay, so it is a constant term. I can subtract also, I can add also. So I can remove this term also. Now you see, I have how many terms? 3 terms. Okay, so I have 3 terms. One is the kinetic energy of the electron, electron ion interaction, electron electron interaction. Okay, now if you see my first session, I told electron, which term is most important here? If you listen properly my first talk, which term is very important? Huh? Which term is very important here? Most important. Huh? Okay, so there are 3 terms in the Hamiltonian. Okay, which term is the most important in the Hamiltonian? No, in no, I am telling, suppose even transport. Okay, let's make it little easy. For transport, which term you feel is most important? No, see, the question is, can I tune the electron motion? See, electron motion is not tunable much. Okay, electrons are very point particle. Okay, I cannot tune them because they will move. It's a free particle, it is moving here and there. Okay, and I want something tuning parameter. Okay, always in condensed matter physics or material science, okay, we always talk about this term. Okay, whatever field you choose, suppose superconductivity, superfluidity, transport, okay, always electron phonon coupling is the most important. This is actually different way to write electron phonon coupling. Okay, so electron, it is a phonon. You will see always all the phenomena occurred is because of electron phonon coupling. Even superconductivity, you may think that it is a Cooper pair, 2 electrons are coming, but the 2 electrons are coming closer because of the phonon. If phonons are not there, 2 electrons will not come closer at all. Okay, so that's why this parameter is very, very important. Okay, and this is the kinetic energy of electron, and this is the electron-electron repulsion. So this is the attractive potential, this is repulsive potential, and anyway kinetic energy of electron. is there. Okay, now I will show you. Today we will calculate what is the value. So now I know the Hamiltonian. Okay, so I know the Hamiltonian. So this is my actual Hamiltonian. So you know this also. This is the time independent Schrodinger equation. Okay, so psi. Now H I know. Okay, now I need to find out. Like I need to find out. Use this equation. What I don't know here is the psi. Okay, I need to find out the psi. Okay, so if I know the psi, if I operate my H on psi, okay, I will get my energy. Okay, now small approximation I do. Suppose this is my wave function. So suppose one hydrogen atom you are solving. Hydrogen atom you are solving. So this Hamiltonian will be for hydrogen Hamiltonian. Okay, this wave function is maybe hydrogen 1s orbital wave function. You operate on this. Suppose it is in 1s orbital. Then what is the energy? What is the value of this energy? You all know, 13.6. Okay, so now a DFT or material science, in DFT what we do, we find out this Hamiltonian, we find out this wave function. That's all. So our motivation is to find out Hamiltonian as well as the wave function. Okay, now so this is theoretical. Okay, now every material is different. Suppose you see iron. Iron is different than sodium. Okay, so this Hamiltonian of iron is different than Hamiltonian of sodium. Okay, or Hamiltonian of hydrogen is different than Hamiltonian of helium. Okay, what is the difference? See, remember, kinetic energy of hydrogen and kinetic energy of electron in hydrogen and kinetic energy of electron in helium, both are electron. So it's not much changing this term, because how electron movement in the hydrogen and how electron movement in the helium, it will not change much, because electrons are electron, whether it is a hydrogen electron or helium electron is almost same. Only difference is their proton number. In one place there is one proton, another place is the two proton. So that also comes here. That's why I told you this term is most important. Okay, because this contains your nuclear term. Okay, how many protons are there? Okay, so that tune your potential energy, and that actually tune your Hamiltonian. Okay, now the question is, I told what is the Hamiltonian for this system. Okay, so now I need to construct the Hamiltonian for this system. For that, now I need this crystal information. Okay, now I choose Fe. Fe is iron atom. So this is, I chose a simple demonstration. For today's demonstration, I choose iron system. Yeah. Okay. So I choose a simple system. Now you see, you know lattice parameter, right? What is lattice parameter? To lattice point or lattice parameter, I can call it. Suppose you have a periodic arrangement of atom. Suppose this is one atom, this is another atom, this is another atom. So suppose this periodicity is A, because after A it will repeat. Okay, so that is my lattice parameter. If my periodicity is 2A, then this is my lattice parameter. Okay, so now that information I should put in my Hamiltonian. What is my lattice parameter? Okay, so that important is there. Okay, first doing all these things, what is this package? This package is called Burai, Burai. Okay, this package is called Burai. You can see there Burai 1.3. Okay, of Quantum ESPRESSO. So the simulation package is freely available. You can just install it and run it. It is very easy to install as well as run. Okay, there are YouTube videos. It is Windows. Yeah, it is Windows. So If you want to do research, then don't do in Windows. Okay, this is just for today's demonstration. Okay, if you want to do research, go it to Linux based, because otherwise your machine will collapse. Okay, if you do it in Windows. Okay, so now see here, you know Bravage lattice, you all know Bravage lattice. Okay, so now if I click on this, see there are different types of Bravage lattice. Now you have to feed the data, your crystal is in which lattice. It is simple cubic, okay, body center, face center, hexagonal, whichever it is, you have to feed the data. See, this is very easy, okay, but when you do in Linux, these things will, information will not be given, you have to put in your hand. Okay, that also I will show at the end. Okay, so these are all crystal lattice, so you feed it. So suppose for me, I will feed the easiest one is the free. Okay, so if you put it free, you have to give your data by hand. So these data are there. Okay, free, no, there is no physics. It is just they made it. Whoever developed the crystal, they made it like, suppose if I put it free, that means I am constructing my own lattice. So they will not construct my lattice. Okay, but when I put it body center, they will assume that I have to give two position in the sense, suppose if I give here 0 0 0, they will assume that there are all the 8 atoms are in the corner. Okay, because 0 0 position is same as this position, this position, this position, all the 8 positions is I think you know that, right? If it's 0 0 position, okay, these all positions are equivalent, and 0.5 0.5 0.5 it is a body center, I mean. Okay, for body center, if I give 0.5 0.5 0.5 position, that means my this position is filled. Okay, so when I put a free, that means I have to give all the information, they don't know anything. But when I select it to that one, see, when I do the simple cubic number, okay, now you will be little surprised when I go to face center. Crystal completely changed. Okay, so when you go to the face center, actually it is same like a see, now that is the beauty of crystal structure. Okay, suppose this is a crystal. Okay, suppose this is your hexagonal lattice. Okay, now there is a concept called primitive cell, you know unit cell, okay, you know supercell you don't know, you know Wigner's cell. Okay, so the concept will be clear. Okay, suppose I want to know the primitive cell. Okay, what is the primitive cell? What is this point called? Lattice point. Okay, now I can add atom associated with it. Okay, if I put atom, it is called basis. So you know in solid state physics, lattice plus basis is equals to crystal. Okay, so suppose this blue ball is not there, that means atom is not there. Okay, now forget about atom. Okay, when we talk about crystal, we don't consider the atom, we only consider the lattice points. Okay, so we consider lattice points. Okay, now suppose if I make a box like this. Okay, now if I repeat this box, I will get all the points. Okay, so this is called primitive cell or unit cell. Why? One. Okay, so suppose my cell contains only, suppose if I do that also, this is primitive cell or unit cell? Huh? Primitive cell. Okay, so that concept you should have clear knowledge. Okay, primitive cell means you should have only one lattice point within that cell. See, this is 1 by 3, 1 by 3, 1 by 3. This also 1, but even I can, for cubic lattice I can make a cube. Okay, but suppose if I have 2 lattice point inside a cell, that is unit cell, not primitive cell. Okay, and Wigner's cell is little different. Wigner's cell is called, you make a junction between all the point near to that and make a half of it perpendicular line, plot a perpendicular line on that line, okay, and you connect. So that will be called a Wigner's cell. Okay, see now all these are cell only. This also one cell, this also one cell, this also one cell, but the name is different. Okay, so now in crystal or in material science, okay, which cell to consider? Question is, I should start my calculation with primitive cell or unit cell or Wigner's cell or supercell. Okay, that completely depends upon your calculation easier. Okay, remember whatever calculation I will show, these are all very high end calculation. High end calculation in the sense you need supercomputer to run it. Simple computer it won't run. Okay, it will crash your laptop. Okay, so don't run in your laptop. You can run just simple 1 atom or 2 atom, but in research you don't run. Okay, you need supercomputer for that. Okay, so now when you now transform, see, same crystal I am showing in different way. Okay, that's all is here. All are same crystal. It is a Fe crystal. Okay, but it is shown as different FCC form, simple cubic form, body center form. So the way looking at is different. Okay, so that's why the concept is when I move to the cubic FCC. Okay, my simple structure looks like this, but it is same crystal, Fe crystal only. So for my understanding or your understanding, I'll keep it in simple cubic only. No, it is not mistake. It is same system like this. Okay, it is same system like this, but I am looking at my body center in the FCC form. My body center crystal, this is my body center crystal, but I am looking at it in FCC form. No, it is body center. SC because, but if you go down, no, one second. It will show, one second. Yeah. See, in the cell, it was simple cubic. Okay. So simple cubic is generally I should have only one atom at the 0, 0, 0 position. But see, I have two position. Yeah, it's correct. Okay. So if I have simple cubic, then I won't have body center position. Okay, so although it is there written as simple cubic, but I have by hand I put this 2 atom position. So when you select 3, then only it will ask us to give the number. Okay. Then I select it as simple cubic, the 27. Even when it is taking the data, it is clear. When you make it cubic, select. This automatically vanishes. No, see, that's what my crystal is. Okay, then I have to go little back. Okay, so what? Huh? Hmm. Hmm. I understand. Huh. Yeah, yeah, I understand. I understand. The see, okay. So then we have to go little behind. Okay, suppose we have simple cubic. When you choose simple cubic, by default we choose that this atom is not there. Now you have to see what is the simple cubic. A equals to B equals to C, alpha equals to gamma 90 degree. Okay, so when you put simple cubic, they assumed A equals to B equals to C, and your A value is enough. You do not need to give B also, C also, and when you put simple cubic, your alpha, beta, gamma all are assumed to be 90 degree. Okay, now when you go to free, that means you have to give by hand. That's why when I put simple cubic, all this freezed out. I do not need to give, just I have to give one, is that this A, B, C, everything is over, not required. Now when I give the free, but you didn't understand when is FCC. Huh. Huh. Hmm. Hmm. Okay. Hmm. Simple cubic. Because my CFL, whatever crystal information I gave to this software, this atom is present. No, but Fe is in body center position. No, see, that's what it is not like that. They do not. Okay, so see, these are all. Don't think as a it is a physics they are doing. It is how they have made their software. Okay, there is nothing behind the physics here. Physics is I will come later. It is how they have modeled. It is a model. So when they design that software, okay, that's what it is. When you do the Linux based, it is easy to understand. But here nobody is using Linux, so huh. No, 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 no. Okay, so it is like what I am telling here is like suppose this crystal structure. Okay, this crystal structure it is a F is body center. Okay, but body center that is zip file is feeded. Okay, to that simulation. But now when you want to see this, okay, whether you are seeing it as a free space or simple cubic phase, they will see they cannot change crystal structure because crystal is always same. Okay, now the representation will change. See, that's why I show you this. This is a hexagonal lattice. Hexagonal lattice is not going to change. Only my primitive cell, unit cell, and Wigner says cell, the way representation is, that is only changing. It is not that when we go from the primitive cell to unit cell, my hexagonal lattice will become tetragonal lattice. No. Geometry only we are talking. Hmm. Hmm. Okay. Does not matter. It is a lattice. It is lattice. Lattice. Huh? Huh. Okay. Okay. See, this is a BCC. This is a BCC. Huh? No. Hmm. Hmm. Where you weakness cell. Okay. That comes when you, yeah, 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 yeah. So Wigner cell knowledge we use mostly when you study the topological study. Right now we are not, see, no, we are using there also, but when you look at your crystal in terms of topology in the sense geometrical point of view, that time Wigner cell considering Wigner cell will give you better prescription. than considering primitive cell and unit cell. Correct. That is easiest way. By Wigner says cell, it is very complicated. So it is no, we are doing. When we study the topological insulator and everything, we use Wigner says cell. But for time being, this is very simple things. We don't use this knowledge here. Hmm. 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 Okay, yeah, that is not usually like we do not use Wigner cell concept very frequently. Very particular step we use it. Okay, that is not like, see, when I go to this structure in terms of body center or in terms of simple cubic, you can easily understand. Correct? It is looking like a body center. When I went to FCC lattice, it looks different. So did you understand anything out of that? So my simple things, I made it complicated. Okay. Correct. So when we see the material science, when we call ourselves is a material science, we try to simplify the system. Okay. When my crystal structure is simplified in the Wigner cell, we'll go to Wigner cell representation. When my crystal structure is simplified in primitive cell, I will be in the primitive cell description. So right now, my crystal structure is simplified in SC or body center. That's what we'll do all the calculation in the SC and body center. Okay, but I will see when you do the research, I will ask you to keep it in free. Because when you keep it in free, everything is in your control. Okay, so in your control in the sense, your lattice parameter. So this is your lattice parameter. A, this is B, this is C. That is a matrix. Okay, it is called cell parameters. Okay, ABC is equal. Okay, so that you have to give for your crystal. Okay, suppose you are doing for sodium chloride. Okay, so then you have to give sodium chloride lattice parameter here. Okay, suppose your crystal is not cubic, it is hexagonal. In that case, there will be the entry. So for simple cubic, it is all are 0. Only diagonal term will be the non-zero. When you go to hexagonal or suppose if I call it orthorhombic, my crystal structure, where the change will be orthorhombic. Suppose for orthorhombic crystal structure, where will be the change here? What is orthorhombic lattice parameter? How it looks like? A equals to B. Now, A not equals to B, not equals to C. For tetragonal, A equals to B, not equals to C. Correct? So for tetragonal, only change will be here. So that is in your hand now. You can change it. I can change it. I can change. I can add. So I will request you keep it always that one as free, because that is in your control now. You can change every parameter here before running. And when it is orthorhombic, your A not equals to B, not equals to C. When it is hexagonal, these values also will be some non-zero values. So that you can add. So suppose somebody is experimentalist, they can produce their crystal structure or their sample. You can get from them what is the A parameter, okay, and you put it here. Is it clear up to this much? Okay. So lattice parameter is designed. Now I'll give this. So this is my Fe. So since I consider Fe atom, okay, so that's the Fe, and this is the mass of Fe, and this is the called, what is written, pseudo potential. Okay, so potential, you know, potential is nothing but, I told here, this is the electron ion interaction and electron electron interaction. Okay, so this information is there. Okay, so since it is technical session, I will not go to much science physics of it. Okay, I will just demonstrate you how you can run it. At least if when I will not be here, you can run it. Okay, so this is pseudo potential. So that I have given. So if you go little down, so these are also technical things. This is called pseudo potential type. It is USPP, that means ultra soft pseudo potential. Why is called ultra soft? Again, technical term. Okay, there are so many pseudo potential available. One is called non conserving pseudo potential, ultra soft pseudo potential, projected augmented pseudo potential. Out of all three, we are considering the ultra soft pseudo potential. That is up to you. You can choose anything. Okay. This is called exchange correlation functional. Exchange and C for correlation functional. It is PBE. This again, it is a technical term. PBE is a three scientist name. Pardue, I think, Bruke, okay, Ehrenhoff. These three scientists, they given functional. So what is this functional actually? New scientists came and they gave the potential data. So different new scientists came and they gave their parameterized. Okay, so that parameterized is this. Okay, and they used cutoff, wave function cutoff and charge density cutoff. These are the cutoffs. Is simple like suppose I have a nucleus and I have an electron. Okay, I have a nucleus and I have an electron. Now this cutoff will allow me to, okay, suppose I have a hydrogen atom. So for hydrogen atom it is easy because they have only one electron. So that electron only have to consider. But now suppose you have a lead element, lead. So what is the Z value of lead? Z, atomic number of lead, 82. Now they have 82 electron. Okay. Now will you do your Schrodinger equation, or it is in DFT field it is called quantum equation, both are same. Okay. Will you solve the Schrodinger equation for all the 82 electron? No. Okay, because all the electrons are not taking part in the conduction or in your physics. So only you will consider which electron? Valence electrons. Core electrons you don't consider. So now how many valence electron will consider? That is up to your hand. I will consider only, suppose I am considering lead. So lead of out of element, I think it is 6s2 6p4. Now I will consider only 6p4 or 6s2 and 6p4 or only 6x2. That is up to me now. Okay, and that designed by the, so how many electron I will consider? Okay, out of 82 now I have to consider. So if I go with the lead, suppose, okay, lead. So I have or core electron, then finally I have 6s2 6p4. Now it is my choice. Okay, all my 6 electron, valence electron 6 electrons, all are contributing, or only one is contributing, only 2 is contributing. That is in my choice. So depending upon that I will fix this data. So that is again technical. Those experienced people will put those data. Okay, so that for that you need 5 years, 6 years of experience. Okay, how to choose this data? You have to do PhD for that. Okay, so next is the atom. Contributing, you can consider transport. Since I am in transport field, you can consider for transport. Suppose you are considering for superconductivity, then you can consider for superconductivity. It is general. Suppose you want to study catalysis, then it is for catalysis application, but your Hamiltonian will not change. Whatever I am telling here, it is very like a fundamental, that is will remain. Only which application you want to see, depending upon that your cutoff and everything will change. Okay, but the fundamental concept will remain always same. Okay, only technical points will change. See, one example I will give you. Yeah, this number, these names. Okay, so since you asked this question, pseudo potential type, ultra soft pseudo potential. I told there are projected augmented pseudo potential also. Now, when I study magnetic property, I will use it ultra soft pseudo potential. When you study non-magnetic property, I will use projected augmented plane wave. Now, if you ask me question, sir, why I will use it? For that, you need to go little beyond. Okay, so that is That's what, all these details are there. Which application you want to study, depending upon that you have to change all these parameters. Okay, now if you want to study suppose superconductivity, superfluidity, and suppose core electron you want to study, core electron phenomena, in that case you have to go to different pseudopotential which consider core electrons also, and you have to use the cutoff depending upon how many electrons you want to consider. Okay, 4 electrons to be considered. So this value will change for all these things. Okay, so I am not going to that details now because I don't have much time. Okay, so anyway, so till now I have fixed my cell parameter, which element, what pseudopotential, what is the cutoff, that I have fixed it. Yeah, so that is, so my geometry. So whatever I did, it is geometry part. Okay, now come to SCF. Okay, you can click here. Okay, now if you go to the SCF, the full form of SCF is self-consistent field. What is the self-consistent field? It is, okay, so see, I told you, have you heard this term self-consistent? Then it will be clear. Have you heard this term self-consistent anytime? No. Okay, so suppose see, I told my Hamiltonian is known, so this is my Hamiltonian. My wave function is not known. Okay, suppose if my wave function is not known, okay, how to find the wave function? No, you have studied, in those who are in MSc 2, they know. Suppose you don't know the wave function, how to start with the wave function? Trial wave function, variational principle. You have done variational principle. Okay, so you start with trial wave function. Suppose this is my trial wave function. Okay, sorry, this is my trial wave function, and I will take the expectation value of Hamiltonian with respect to the trial wave function. Okay, so that is my expectation value of Hamiltonian with respect to trial wave function. Okay, then what I will do, I will take the derivative of this value with respect to psi and make it to 0. So that will give me actual wave function of the system. Okay, so that is called variational principle. You have studied it. Okay, so no, my wave function is not vanishing. These quantities should go to 0. 0. No, I have to make it, see, okay, so my wave function, suppose suppose I'm considering, okay, so suppose this is my hydrogen atom I'm doing. So I know my hydrogen atom wave function. So hydrogen atom wave function is R divided by A0. Since we all know hydrogen atom wave function, we can start with that. So e to the power minus alpha R by A0. What is A0? Bohr radius. And what is the R? R is the position of electron, and we know that this is the electron is in their 1s orbital. Okay, this is my true wave function, but variational principle tells that choose a wave function like this and put a variational parameter alpha. Okay, put a variational parameter alpha. Okay, so this is my trial wave function now. Okay, and you take this wave function and put it here. Okay, now if you do the wave derivative of that, you will see that since it is a proper formula, like it is a proper wave function, my alpha value will turns out to be 1. Okay, so after doing all the calculation, alpha value has to come 1, because that is the minimization of, actually this is the minimization formula. Okay, we are minimizing our wave function so that I get the actual wave function. Now same hydrogen atom, if we start with the, instead of considering this trial wave function, if I start with this trial wave function, I can start my trial wave function can be anything. Okay, in that case I will never end up with this wave function. Okay, because my initial choice is different. Initial choice was little wrong. I will not tell exactly wrong. It is very different than this functional form. So I will never get my actual 13.6 electron volt whatever is there. I will never get that expectation value. But for this case, I will get it. Okay, that's what this is the one way to get the wave function. Okay, but in DFT we don't do that way. In DFT we do self-consistent methodology. What is the self-consistent methodology is? It is also variational but little different way. What we do, we start with the trial wave function. Okay, and we start with the trial wave function. Okay, and we calculate the expectation value. We do the variational principle. We get my second trial wave function. Maybe you can put it 1. Again you put it here. Again you calculate the expectation value. Again you do the derivative. Okay, so every time you will get one energy, E1, E2, E3, and your wave functions are getting modified every time, every iteration. That's called self-consistent. They are changing their energy, their wave function. This iteration will run as long as your E2 minus E1 minus E2 will give you, or will not be less than some 10 to the power, that I will fix it, 10 to the minus 8. Unless or until that will, so this my last iteration minus my previous iteration will not come to some convergence value. Till time, that time my iteration will go on. Okay, when it will reach the convergence, with that value I will schedule it. I will put it 10 to the power minus 8. Okay, when I put this value, when it is achieved that level, my calculation will come out. I will show you how it is running. Okay. Yeah. So that's what is DFT doing. It is called self-consistent field. Now this is the input file of self-consistent field. Okay. This term is called restart mode. Restart mode in the sense, suppose you start, today you did 1 hour calculation and you stop it. Tomorrow again you want to start from the last step. So you have to make it yes or no. Okay, if you make it no, they will start always from the first step. Okay, maximum time. Some calculation when we start, it is never ending. Okay, so my calculation will run like 1 year, 2 year. I do not want. I want, if my calculation is run up to 1 hour, that much only I will go. Okay, so this is the second I will specify. These are all technical things. Then force calculation, stress calculation, technical things I can turn on. Okay, this is not important. Again, the cutoff frequency, if you see, they are also, that value was there, 25 to 25. These things were there. Okay, I will not go much. Then yeah, so now total charge. So I know my this system total charge is 0. Okay, total charge is 0 for this system. So I will not specify. Suppose I want to add one charge in the system, so I will put it 1. If I make it charge system, so I will add 1. That means 1 electron is added in the system. Okay, so I will put it. Since I am not doing any charge calculation, I will keep it 0. If nothing I mention, it is 0 default. Use symmetry. I will use the symmetry. I can turn off also. Does not make any sense. Okay, this K point. Okay, what is the K point? Okay, see, I am doing this. When you do the expectation value, okay, actually this is nothing but correct. This is nothing but psi star h psi. This is integration, and this is the integration limit 0 to, okay, I will put it r, since we are always considering, if it is r, then only it is 0 to infinity. If it is x, then it is minus infinity to plus infinity. Okay, so now when you do the integration, you all know there are trapezoidal method, right? You had trapezoidal method. trapezoid integration method, numerical techniques, trapezoidal method. Okay, then there is Simpson 1/3 rule, Simpson 3/8 rule. Okay, so there we have some, suppose I want to calculate some integration. This is the integration, so I'll make it division and I'll calculate my function at all the points. See, remember, these are all numerical technique I'm doing, numerics. Okay, so I'll specify my k points. So these are the k point, how many k point I want to. Okay, so it is another way to tell. You all know Brillouin zone, you all know Brillouin zone. So I'll segregate my Brillouin zone in 4/4/4 points. Okay, as you give more and more points, your integration value will be more and more accurate, but your calculation will be more and more time consuming. Okay, so since we are doing for demonstration, I'll keep it 4, 4 and 4. And now occupation. Yeah, so there are two options are there, smearing and fixed. Okay, fixed means they will consider this. It is how your Fermi-Dirac distribution looks like. So Fermi-Dirac distribution looks like this. Correct? Is a step function. Okay. When you make it fixed, that means you consider this distribution. When you give the smearing, you are considering this distribution. Okay. So that's what you are. See, everything is modeled there. Just putting the that. Okay, I am just tuning my physics. Okay, so for the time being, I will keep the smearing. Then smearing is the Gaussian. So there are also many options. Then these are all again scientist name. Everybody gave their functional form, how distribution looks like. Okay, so it is Gaussian. Gaussian, you know, all is a Gaussian form. Okay, so I will go with the Gaussian form. Since everybody knows it, I will go with the Gaussian form. Again, this is the width, smearing width. Okay, what I mean here, suppose this is a, so when I wrote like this, that means I assume it is a Gaussian form. Now every Gaussian form has a width, and that width is here. So if you increase your more and more width, that means your calculation will be more and more faster but inaccurate. As you go less and less width, it will be more accurate but more time consuming. So everything is up to you. Now second data is, I wrote here, right, 10 to the power minus 8, some convergence threshold. That value I kept it here, 10 to the power minus 6, just for first calculation. I'll show you, okay, how the calculation works. This is the initial guess. I told, right, wave function, trial wave function. Now how to choose wave function? Okay, so there are many wave function is given initial. So you can start with atomic wave function, you can start with random wave function, you can make random plus atomic wave function, or you can make your own wave function. That is option also there to given to you. That's fine. This is diagonalization. Okay, so this is Hamiltonian Hamiltonian matrix. You know, you don't know Hamiltonian matrix. Okay, so Hamiltonian Heisenberg formulation, you know, in quantum mechanics, right? Heisenberg formulation. So Heisenberg formulation consider the matrix formulation. So since it is a matrix, they have to diagonalize the matrix, and these are the people. Okay, so Davidson is one of the person, he showed how to diagonalize the matrix. It is a Davidson mechanism, and CG means conjugate gradient. So these are all the way to diagonalize the matrix. So those things we do not need to know. It is default set. So initial guess, everything done. Then magnetization. Okay, so magnetization, now there are collinear. Yeah, so there are three parts. Now suppose if I consider sodium atom is magnetized? No. In that case I will choose the non-polarized. Suppose I use the Fe atom. I know Fe atom is an ion, it is a magnetized. So I will go with the collinear. Collinear in the sense it has a spin, it has up and down. Okay. If I go with the non-collinear, it will come into the picture when you have heavy atom, that means spin orbit coupling. That means your spins are not up and down, they can couple together, or they can make a x axis. So you know, right, SZ component of the spin. Spin has SZ, SX, SY. So when you do the spin polarized calculation, it has only SZ component. When you go to non-collinear, it will have SX, SY, and SZ. That means spin can rotate now in any direction. Okay, so there those things I can specify. For my simple calculation, I will keep it non-polarized. See, DFT is very easy if you don't understand. Okay, but when you try to understand, it is very, very complicated. Okay, because everything is given to you. Now you are choosing, but if your choosing is wrong, you will get something very wrong result, and it's everything is wrong. See, when I put my non-collinear, suddenly see spin orbit coupling pop up. Okay, when I put it non-collinear off, the spin orbit coupling is not there, or it is not required. Now fixed magnetization. So when if I put collinear, all my magnetization data will pop up. Okay, so this is also fixed method, which magnetization you want to give. Okay, so you can just click there. Okay, so you can fix here your magnetization. Now you have to choose, okay, Fe atom, what is the magnetic moment of Fe atom? It is Bohr magneton or mu b, 1 mu b, 2 mu b, that you can fix here. Okay, those things. So for the time being, I will not go into that. Okay, I will go to non-polarized calculation. Okay, yeah, so then next is GGA plus U. Okay, so GGA plus U tells that, okay, suppose Fe atom, suppose 2 electron is there in the d orbital. See, 2 electron in the s orbital is different than 2 electron in the d orbital. What different? S orbital electrons are delocalized, so electron can move anywhere, but d orbital electrons are not delocalized, they are very, very localized, and since they are localized, electron can repel each other. So this is the U term. U is their interaction, repulsion. That value I can specify. What is the value? So here, if I make it yes, I have to give some value. Okay, I can give 1 eV, 2 eV, 3 eV. So that also experience. You need to gain the experience, then only you should choose these values. Okay, so for the time being, I will keep it no, because why I am keeping everything no? It will be easy to calculate because I have to complete. Okay, so Harvard U will go. Yeah, so my SCF is done. Okay, so my geometry, I prepared my geometry, I did my SCF calculation. SCF means electronic part, I have did it. Now I will run this. Okay, for the running, you come here. Okay, so whatever I have specified there, if you go to input file, you can go to input file. See, whatever I specified there, everything is written here. Whatever number I put it there, d Gauss value, some values I gave. N spin is 1. Why n spin 1? Because I consider non-spin calculation. If I put it n spin 2, it will be polarized calculation. That means spin is there. If I put n spin 4, there is a non-linear, non-collinear calculation. Spin orbit coupling is there. Okay, so all these things you can specify values. Okay, then you can go to run option. Okay, so you can just run it. Okay, so again we are doing SCF calculation. Okay, so I have self-consistent calculation I am going to do. I can do optimization calculation. I can do MD means molecular dynamics calculation. DOS means density of states calculation. Band means band structure calculations. So I can just specify one of them, okay, and run it. So for the time being, I will do SCF calculation. Processor. Till now, my laptop has 16 processor. Okay, I will be using 4 out of them. Okay, so MPI means it is a parallelization package. Since my laptop has parallelization, so they will, out of 16 processor, they will use only 4 processor. Okay, because it will scale up my calculation. That is localhost. I'll specify it. Yeah, it started running. Before just few seconds, it was red, right? That means it was running. When it shows green, its running is completed. Okay. So it ran. Go to the result. Okay. So if you go to the result, so first one is of my input file. First one is my input file. So I can, so SCF is there. So I can go to the, yeah. So that is my output, whatever I ran. So this is my output of running. You see, I specified 4 processor. That's why it's showing 4 processor. If I give the 6 processor, it will show 6 processor. Okay. Since I gave 4 processor, that's why it became very fast. And these are all, since I started with, I think, free, I started, that's why it is showing 1. If I start with simple cubic, it would have been 2. And these are the lattice parameter, whatever I specified. Lattice parameter, it is in atomic unit. Okay, I think I gave 2 point something. So 1 atomic unit is 0.532 angstrom. Okay, so that you can convert it. This is the atomic unit volume, and all this cutoff and everything is mentioned here. So the calculation will start after. So these are all specified. I have specified. Yeah. So this is the iteration. This is the first iteration. So I showed here, right? So you start off with your trial wave function, calculate the expectation value, do the first derivative, minimize that, and again you minimize the wave function, again you feed that wave function, again you do the self consistent. So it is a iteration till you get the result. So this is my first iteration, and I used my Davidson, I used David there. Okay, Davidson algorithm I used to diagonalize. This is my cutoff, everything whatever I used, and finally I got total energy minus 111.38 Rydberg. This energy is nothing but this energy. Okay, so you see, I started with my Hamiltonian. I did my calculation. Then I choose some trial wave function which was random or atomic nature. Okay, then I minimize my wave function. I got my final wave function. I operate my Hamiltonian on the wave function, and I got my energy. Okay, so every iteration my energy will change, and finally I will end up with the minimum energy. So you see, this is the first iteration, this is the second iteration. So my energy is changing. My iteration went up to this is the 9th iteration. CPU time, it took 2.7 seconds to run. Okay, sorry, so 10 iteration it went, 11th iteration, 12th iteration, till till 19th iteration it went. Yeah, so it went 19th iteration. After that it converged. I got the converged result. I will show demonstration that part also. So end of self-consistent field calculation, SCF calculation. That means my iteration is done. Then they will write, for every k point they will write the energies. Okay, so that part also written. Finally I got, and if your calculation is done, it will show job done. If there is a mistake, it will not show this. Okay, so if your calculation is properly done, okay, there is no mistake, then it will show job done. Okay, so your SCF calculation is performed. Okay, so my energy is, calculation is done. How much time I have? 15 minutes. 3:30. Okay, then I will take another 2 minutes. Okay. So now if I choose band, and if I do the calculation again I have to choose the band, again I have to go run, okay, and again I have to go the result, okay. So you run it and result, if you go, see, already before coming here I ran everything, I just checked it, so all my results are there, okay. So band's results are here, DOS results are here, okay. So just I can click it, okay. So this is my band structure. So why two line came, one is red, another is black, is because of spin up and spin down, because Fe has a spin up and spin down. If you start with the sodium, it will not show, it will show only one band, okay. So so since it is metal, that's why there is no separation between valence band and conduction band. But if it would have been semiconductor, there would have been clear division between valence band would have been down of the, so this is my Fermi level. My valence band will be down to the Fermi level and conduction band will be the up of the Fermi level. So this is my band structure, okay. So now if I go DOS also, so it is my density of states. Again this is the Fermi level, below the Fermi level it's valence band and conduction band, but since it is metal, there is a superposition of everything, that's why we have finite bands in the Fermi level, okay. So that way it is the very simple way to demonstrate, but when you do in Linux in for research, it is very, very complicated, okay. So that's all, okay. So other than this also, if I go here, okay, so geometry I showed you, SCF I showed, optimization I didn't show, molecular dynamics I didn't show you, DOS and bands I showed, okay. So till now in Burai package these things are already implemented, okay, but phonon calculation is not implemented in Burai. So when you go for phonon calculation, you have to go to Linux based system, okay. And time dependent density functional theory is not developed, Nudge elastic band is not developed yet, okay. So this is all about the demonstration of quantum expression, okay. So yeah, so thank you. So any question? So should I turn off? Any question? Anything? You got an interest in material science or condensed matter physics? So if you are interested, I can help you to install in your laptop, okay. So you can install it, okay, then you can run. And if you want to learn more, you can visit our university also, okay. So you can come to our lab, okay, we'll teach you more details, okay. Right now just demonstration I did, okay. So you can learn also more, okay. Thank you then. No? Okay. Correct. See, yeah. No, actually the problem with the DFT is that it is not exposed to the student. Okay, so students do not know it. See, whatever I showed here, it is very fundamental, okay, fine. But actual scenario starts after that, okay, because when you do the quantum computing, okay, machine learning and artificial intelligence, that starts after that. Okay, so those part I didn't touch, okay, because this material I can use as a quantum computing material. Okay, I can use all this spin now, I can play with the spin. Right now I didn't show anything, okay, so I can play, I can put one number, two number, three numbers, so I can play with the spins, okay. So anyway, we'll discuss more if I get more time to come here.